So in this video, we're going to talk about some of the basics of vectors and go over how we can use the mathematical properties of them to figure out what the net force is on an object. So again, a couple quick definitions for a vector. Represents quantities that have both magnitude and direction, how much and which way something is going. Okay, it's illustrated with an arrow, which allows for you to kind of visually represent the mathematical value and the direction. So the keys are that the length of the arrow indicates how much, or the magnitude, and the direction it's pointing is going to represent the direction of that value. So we've dealt with some vectors before, things like velocity, displacement, and acceleration, and now we're adding force into the mix of things that have both a quantity but also a direction that they are going. So some examples, just real quick. Again, we had our velocity on the x-axis and our velocity on the y-axis from our projectile unit that we were using. Again, telling me how much the velocity is going in which way, okay, both by the length and by the direction of the arrow. For forces, we're going to have kind of the same idea. Might have a box, and might have somebody pushing on that box, okay, being the applied force. But if it's on a table, we've also got the weight acting on it, and we've got the normal force coming from the table. So we're going to have this combination of forces acting on things illustrated by the vectors that are there. Okay, again, how much by the length, direction by the direction of the arrow. So here's some basics of vector math. So vectors can be added, subtracted, multiplied, and divided. Okay, we're not going to worry about multiplication and division at this point. We're mostly going to just worry about subtraction and addition. Okay, we'll see how that plays out here. So say we have a 1 Newton vector going to the right. So somebody's pushing on a box with 1 Newton of force. Then we have a 2 Newton force gets added into that, right? So now we have 1 Newton to the right and 2 Newtons to the right. Well, that means in summation, we're just going to have a 3 Newton force to the right. Okay, the two forces will add together. We'll end up with a greater net force at the end. Now we can also do subtraction, whereas if we have 1 Newton force to the right, then we have a 2 Newton force to the left. Okay, all of a sudden at the end of that, we end up with that 1 Newton force to the left. Okay, so how they get added is through what's called a head-to-tail addition. So we can deal with this on different axes a little bit easier. So basically what we're going to do is we're going to take the components, the small parts of the sum of the vectors, and come up with the resultant vector. Kind of like the sum of the two, the representation of all of the vectors together in one vector. Okay, that might seem confusing, but it's not too bad. So let's say we have a vector going this way. Pretend that's straight. Okay, say that, and then we have another vector going this way. And let's say this one has a length of 3, and this one has a length of 4. Okay. When we talk about head-to-tail addition, all we're really doing is we're going to go here and we're going to draw each vector from the end of the other one. So I'm going to take this 4 Newton vector right here, and I'm going to draw it in from the end of the 3 Newton vector. Okay, completely parallel to the other 4 Newton vector. Okay, that's why this is called the parallelogram rule. We're going to make a parallelogram. And then I'm also going to draw the 3 Newton vector in from the end of the 4 Newton vector. So here's my 4, and here's my 3. Where those two intersect, that is going to be what's called the resultant. Here is my resultant. Or in the case of the things we've been talking about with forces, that's going to be the net force. That's going to be the direction of the one vector that we could draw that would be the equivalent to the 3 and the 4. Okay, so again, quickly what that means is that 3 up and 4 to the right is equal to, and it's the same as, a 5 Newton vector at that angle. Okay, those two things represent the same type of motion. Okay, this is the one-step definition of these two vectors together. Now we got that to be 5 because, well, it's a 3, 4, 5 triangle from Pythagorean's theorem. 3 squared plus 4 squared equals c squared. So c is going to equal 5. We have 16 plus 9 is 25. Take square root of that, we get 5. Okay, so that's how we can take vectors from a different axis and add them together into a single vector on one axis. Since those two that set of vectors are equal to each other, we can also take advantage of the reverse principle. We can take a vector, the resultant vector, and break it up into its two components. And how this is going to help us is if we have things kind of all over the place, we want to bring it all down to the two major axes, the x and y axis. So for instance, if we had something where a vector was like this, and a vector, we had one force going that way, maybe a wind acting on, we have a boat that's trying to go across a river, and it's got one force acting that way, it's got some drag working on it this way, and then its engine is pushing in this direction. Okay, say this wind here is operating at a 45-degree angle. Okay, what we can do, say here's our water, is we can take the wind force, this one right here, and we can turn it into its two components. Right now we know it's probably going to go off to the right a little bit, but we don't know exactly how much and in which way. What we do is take that wind force and break it down into its horizontal and vertical parts. So to do that, we do the opposite of what we were doing before about saying, okay, let's add them together. Well, let's take this down to the x-axis, and then let's take this over here to the y-axis. And these two yellow vectors are now the two things that are equal to that 45, that wind force vector. So again, we had that one at 45 degrees, and that is equal to these two components that are at 90 degrees to each other, they on the x and y axis. Why would we want to do that? Well, if you look here, this yellow vector right there and this red vector right here are both going in the same axis. We can add those two together. So we would add that red plus that yellow together to get the total vertical force that way. And then we have that vertical force going the opposite direction. And those three become pretty easy to deal with. The other key too is we still have this one vector going this way, right? If we look up above. So once we simplified this one and this one and this one, we'd be left with a single vector going up and a single vector going to the right. And then we would just find the sum of those two going off in that direction. Okay. So getting everything down to the x and y axis is going to be the key. So kind of here's an example of that whole process here. So you have a 6 Newton force at a 45-degree angle, we have a 4 Newton force and a 10 Newton force. The whole goal is to find what is F net. Okay, what is the net force acting on this object? So the first thing we would do here is take that 6 Newton force and we're going to break it down into its two components. We're going to find out what the horizontal part is, and we're going to find out what the vertical part is. Okay. Since this is a 45-degree angle, this is also a 45-degree angle, which means these two sides, we'll call them A, we'll call them B, are equal to one another. So we take advantage of the Pythagorean theorem, which says that A squared plus B squared equals C squared. And since A and B are the same, we know that 2A squared equals C squared. C is 6, so C is going to be C squared. 6 squared is going to be 36. It's going to be 2A squared. So A is going to be the square root of 18, which is 4.2 newtons. Okay. So what does that mean if I redraw this? Well, that means that I have a 4 Newton force this way. I have a 4.2 Newton force this way. I also have a 4.2 Newton force that way, and I have a 10 Newton force straight down. Okay. That's the new representation of what we started with. We took that 6, broke it down into its two components, and now we're going to deal with the fact we have these 4 vectors acting on it. The next part is this becomes pretty easy because the 4.2 and the 4 are going to result in a 0.2 to the right. The 4.2 and the 4.2 up here and the 10 are going to result in a 5.8. No, sorry, that's terrible math. Not 5.8. Let's try that again. Do my math a little bit better there. Oh no, it was 5.8. My bad. A 5.8 Newton force. What's going on? Going straight down. Okay. Now we just need to find the hypotenuse of my triangle, because remember again, we're going to go straight down, over, bam, there's our resultant force. So 5.8 squared plus 0.2 squared equals c squared. So c would be 5.8. And it's basically the exact same as this one because this number is so small. But the end result is it's not going to be perfectly vertical. It'll be shifted a little bit to the right. So, but the net force acting on this object is a 5.8 newtons down to the right. So again, the whole idea is get everything onto the x and y axis first. You can do it as many vectors as you want, it doesn't matter. If you can simplify them down to the x and y axis, if you can simplify them down to something that looks like this, you can always get it down into 2 vectors. And from there, it just becomes find the hypotenuse of your triangle, find the result of those two.